So, we mentioned in the previous lecture that when the model consists of a large number of degrees of freedom, it is algebraically and computationally a difficult task to directly solve the characteristic equation and determine the natural frequencies and the modes. Instead, I think there are some simple iteration procedures which can lead to reasonably good values of the frequencies and the corresponding mode. So, we will discuss these methods which are very useful to designers, and also during the design all the time it is not possible to switch over to a computational program, and therefore, such techniques which can be used and reasonably good answers can be obtained with the help of a simple calculator can be quite often very useful. Before we go directly to that, one more concept we will discuss. Before one can attempt to start the solution process, it is essential to write down the matrix equation of motion, and in some cases that itself may take some time, but with the help of one new concept like influence coefficient and flexibility matrix, even the equation of motion in matrix form can be found out in a reasonably quicker time. So, what is, we will define a quantity Aij as the deflection at station I due to a unit force at station A. So, for an n degree freedom system, the displacement at any instant at the ith station will be Aij, force which is acting at the jth station, summed over j equal to 1 to . So, for a normal mode oscillation, xi equal to capital Xi cosine omega t. Now, the question is that when such a vibration takes place, what will be the forces acting? How do you convert? As a static problem, you can see it is very simple, but a dynamic problem, we have to convert to a static problem by applying D'Alembert's law or D'Alembert's principle. That we have done earlier also. So, at every station, like say for ith station, it is having an amplitude capital Xi with a frequency omega, and that station carries a block of mass Mi. So, what we can do is that we apply or use or introduce the inertia forces at each station. So, at the ith station, inertia force will be minus Mi into omega square. Rather, what we should write is minus Mi Xi 2 dot. So, when you consider, that means at any instant we can use the acceleration of that station multiplied by the mass of the station as the and negative of that. This is the inertia force. We assume that it is being applied at the ith station, and the combined effect of all such inertia forces in the absence of any other force, because it is a free vibration, the displacement at this we can find out. So, thus displacement, which is Xi cosine omega t, will be, which is Xi, will be sum total of A I j Fj. Now, Fj will be minus Mj into Xj 2 dot. How much is Xj 2 dot? Xj 2 dot, if x is equal to this, so Xj 2 dot will be minus, another minus omega square Xj summed over all such j's from 1, or we get Xi is this we can write in matrix form, that means I equal to 1, 2 up to n. So, we can write, or in matrix form, all the equations can be represented. This will be x1, x2 up to xn is equal to omega square 1 1 a 1 2 a 1 n This is the expanded form. In short form, we can write this as x equal to omega square. This is the A matrix, this is the M matrix. Now, this we call the flexibility matrix, because AII represents the deflection per unit load at another station. So, it is nothing but a measure of flexibility, which is just opposite of stiffness, because we can very easily find that according to this definition, x is equal to this, and we know, therefore, x will be the flexibility into force. So, if you invert, pre-multiply by A inverse, this will be A inverse into A is unit matrix. So, this is F. But we know F matrix can be written as this also. So, K matrix is nothing but inverse of A, or A matrix is nothing but inverse of F or K. This is the stiffness matrix, its inverse is the flexibility matrix. We write this as omega square d, where d is another form of dynamic matrix. There is no need to give a name, but which is nothing but A into M. So, this equation we have to solve by iteration technique. So, iteration technique means that we assume some value of x or some modal matrix x, anything, we multiply this. Then by normalizing means maybe one of the terms, like the first term we always keep 1. So, that way when you do it, let us see whether we get back the same matrix or not. Normally you won't get. Then we use the second matrix, the result what we get, that matrix, again we put it here and do the operation again and again. I will explain this with the help of an example. So, let us consider a 3-degree freedom system, and let the system be this. This is a simple 3-degree freedom system, and our objective is to find out the natural frequencies and the natural mode. So, first is we have to determine the D matrix. Now, M matrix is quite straightforward. For D matrix, if you have to find out, we have to find out first the flexibility matrix. Flexibility matrix, let us see what is A11. That is, if you apply a unit load at station 1, what is the deflection of station 1? Obviously, it is only the stretch of the spring, and that is nothing but 1 by K. Now, what will be the deflection of this position if you give a unit load here? Again, it is nothing but the stretch of this due to the unit load which is also passing through this. So, this will be simply as A12 also. Similarly, if you apply a unit load at this location, that is third station, again the stretch of this spring will be same, and that deflection of station 1 will be. Now, on the other hand, if I apply a unit load at 1, only this spring stretches, these things just displace as a rigid body without any distortion. So, the displacement at station 2 due to a unit load applied and station 1 will be same as 1 by k, and that is A to 1. Similarly, if I apply a unit load here, the stretch of this will be 1 by k, and this is moving just like a rigid body. So, the displacement of station 3 will be also equal to 1 by k, which is A. Next, A22. A22 means that if I apply a unit load here, what will be the displacement of this? It is obviously the stretch of this spring due to unit force, stretch of this spring due to unit force. So, is 1 by k, 1 by 2k. That is the influence coefficient A22. And obviously, if you apply a unit load here, the displacement of this will be same as the displacement of this, because this moves just like a rigid body. This spring is not stretched. So, this is obviously A2. At the same time, if I apply a unit load here, what will be the displacement of this? It will be again the stretch of this spring and this spring, which is this. So, this is A23 also. And the only one which is still not determined is A33. That is, if I apply a unit load at station 3, what will be the displacement of the station 3 itself? It will be the stretch of these 3 springs. So, obviously, it will be 1 by k plus 1 by 2k plus 1 by k, which is equal to 1, 2, 2, 4. So, 5 by. So, A matrix can be written as 1 by k. A11 is 1, A12 is 1, A13 is 1, A21 is 1, A22 is 3 by 2, and A23 is 3 by 2. A31 is 1, A32 is 3 by 2, and A33 is 5. This is the flexibility matrix. We also know the mass matrix. Mass matrix will be simply first mass is m, second mass is 2m, third mass is m, and these terms are all 0, because mass matrix is a diagonal matrix. So, this is nothing but m into 1, 2, 1, 0, 0, 0, 0, 0. So, the D matrix is equal to m by k into this into this. The result I will give, it is straightforward. So, thus we are now ready for our iteration process. So, we will write this equation. Omega square d x is omega square m by k 1, 2, 1. Now, first step, we can start with anything, any assumption on x. Iteration process, let us start. First assumption, the x, the simplest let us take as 1, 1, 1. So, this if we substitute here, we will get omega square m by k, one particular case I am writing. One. This will be omega square m by k 4, 5.5, 6.5. Now to normalize, let us always make the first one always 1, because the ratio of the various terms are actually important, not the value. So this will be 4, 1, 1.375, 1.6. So this is the value we get now. So in the second step, we assume x as that 1, 1.375, 1.6. Now, if we apply this, we multiply this by the D matrix, this will be now so to normalize, the first term has to be kept 1, so we write this as if we apply now I will not write the in between things. So third step, we have x equal to 1, 1.407, 1.709. You can see we started with this, but we got back this. So therefore, it is still not satisfying this equation. That means if you pre-multiply this, you will get back that you have supposed to get back, that we are not getting. Now, if we do this now, what we will get? We will get this as 5.523 omega square m by k Now you see, one can easily see that we are gradually closing, that I started with this and came back to something which is not very far from this. Maybe one more step will bring us to the final result. Say let us take the fourth step if I want to make it more accurate, depending on the amount of accuracy one desires. If we use this, we will get so now we consider that we have reached that. So the equation what we had is now fulfilled with this particular mode. Now the equation to be fulfilled, that means if this has to be equal to 1, 1.409, 1.720, then what does it mean? That this has to be equal to 1. If this quantity has to be equal to 1, then only this equation is satisfied. That means your corresponding omega will have to be how much? So omega will be correspondingly 0.425. So and the normal mode is 1, 1.41 say 1. This is the mode, this is the corresponding frequency. Now whatever may be the starting point, 111, we can take 101, we can take 321, we can take 7.5 minus 3, whatever may be the starting point, you will find that we will always converge to this mode and this frequency. It may look like a miracle, but I will show you the reason that why it is happening so. But the question is that which mode is this? Now it can be proved, as I will be doing now, that this is nothing but the first mode or the fundamental natural frequency, and this is the first mode. Why it is converging always to the first mode? I think if that is the question we have to understand, then just we will digress from the iteration procedure for a short while. Now we have seen that omega square d x, say for a particular mode I, this is a particular frequency I, is equal to, here I have not used I, but always remember this is valid only for a natural mode of oscillation, and let that be the ith mode. Or we can write d is nothing but 1 by omega I square for all the natural modes, I is equal to 1, 2, 3 and so on. Now, when we assume something, so the assumed mode shape. Now, assumed mode shape can be always expressed in terms of the first mode, a combination of C1 or if we still further normalize, we can always make this, divide the whole thing by C1, I can make it like this. C2 by C1 is one quantity, say let us call, originally we called them as prime, now I call it as C2, which is nothing but C2 prime by C1 prime. So, it is always possible, whatever may be this assumed value, it can be expressed in terms of a series of all the natural modes. Fine. So, now if I apply this d into x, that means when I pre-multiply x by d, what does it mean? I am pre-multiplying each one by d. Now, since this is a natural mode, when I pre-multiply this by d, I will get 1 by omega 1 square x1 according to this rule plus C2 omega 2 square x2 like that, C3 by omega 3 square . So, now the resulting, if I normalize resulting x, I will get the mode will be somewhat different from the previous one, because these coefficients are different from the coefficients earlier. If I again pre-multiply this, that means if we pre-multiply this again, effectively now again I am pre-multiplying this by d, what will happen? Again when I pre-multiply x1 by d, this term will become so after n such iterations, say this we will get 1 by omega 1 to the power n and so on. Now, we should notice that in general, omega 1 square is much less than omega 2 square is much less than omega 3 square and so on. So, what will happen? That omega 1 square is more than 1 2 square. So, when we raise these things to power to n and n is sufficiently large, So then you will find almost approximately equal to the rest. So therefore, what is happening, the most important thing, that since I think we will do it this way, so therefore, if we make it n to the power, this whole thing is aggregated further. So only these things are far smaller compared to this term. So the predominant term, what we get after n number of iterations, is approximately equal to what does it mean? Forget about this. As far as the mode is concerned, because the ratios of the various terms, it really approaches the first mode, and the corresponding frequency becomes the first natural. That is why we are, whatever may be the initial value, if it is closer to first mode, then number of iterations will be less. If it is very different from the actual first mode, it will take a longer time to converge to the first mode, but it will converge to the first mode. So therefore, this is a quick way of getting an idea about the natural frequency and the first natural mode, not solving any matrix equation, because it involves only simple matrix multiplication, which is much easier, and quick time we can do it. Next, the question comes that if we require to find out the higher mode and higher natural frequency, that means here there will be 3 natural frequencies and 3 modes. We have found only the fundamental one. How to find out the higher mode? So to determine the higher modes, we will take this approach. First, let us keep in mind the very important conditions which we derive. These are the orthogonality of normal modes. This condition we have to keep in mind. Now, any mode we assume can be expressed as C1 into the first mode shape, as I have mentioned just now, C2 into the second mode shape, and so on. Now you see that when now we pre-multiply this by D matrix again and again and again, gradually this term tends to become more and more prominent, because omega 1 by omega 1 square, by which it is being multiplied again and again for each pre-multiplication of D, because of this. So we can express it in this way. So every time we pre-multiply by D, one such term comes, and therefore, as omega is the smallest, this is the largest, and repeated multiplication causes this term to be prominent. If we could somehow make C1 0, then our assumed shape would have started from here. And if we repeatedly multiply or pre-multiply this by D, then the whole thing will converge to the second mode, and we will get the second natural frequency. Similarly, if we could make both C1 and C2 0 by some means, then the whole thing, the next term, it will converge to that which is nothing but the third term. So, in this particular case there will be only 3, so it will converge to the third natural frequency, and the mode shape we will get is third by the same process. So, our objective is now to find out ways and means of doing or making a thing or making x such so that C1 is 0. Now, one thing, if we pre-multiply by if we pre-multiply this, what we will get? All other terms will be 0 because of the orthogonality condition. This is the only term when this is 1 and this is 1. Later this will be 1, the other will be 2, be 0, and so on. And now, so therefore, I will again take this example. This example will give us x1 for mode 1, x2 for mode 1, x3 for mode 1, m1 0 0, m2 0 for a 3-degree freedom system, and when I am not putting anything superscript, it means it is not actually a mode. Whenever it is a mode, it is there. So, this is equal to 0. That is what I am saying, that if I make this equal to 0, since this is not 0, we have said that when both are there, this is nothing but the generalized mass, which is not 0. It can be 0 only if C1 is 0. So, therefore, putting this equal to 0 means C1 is becoming 0. So, this implies C1 equal to 0. So, therefore, if this is nothing but this, and when I am putting this equal to 0, it means C1 has become 0 automatically. And if you expand this, you will get M1 x1 1 x1 or we can write x1 is equal to minus so now we have got this equal to 0 means x1, x2, x3 cannot be independent, because x1 can be written in terms of x2 and x3 using this equation. x2 of course is equal to x2, x3 is equal to x3. So, this whole thing can be written in matrix form x1, x2, x3 is equal to or symbolically we call it S1. Small x or capital X doesn't matter because cosine omega t gets cancelled. Now what has happened? Now we have already solved the first mode, that is always in remember. So these quantities are known. X11, X21, these are all known quantities. M2, M1, and they are also known quantities. So this is a known matrix. And when this matrix pre-multiplies this, right, like this, then it means that the first mode has been swept out as C1 has been made 0. That's why we call it a sweeping matrix. So similarly, C2 can be made 0 by pre-multiplying this by X2 . So when both these and these equations are satisfied, then both C1 and C2 have been stripped out, only C3 is left. So then if we do the iteration, we will go to the third mode. Before we do that, I think so this example if we do, so in this case that means when both are stripped out, that means two equations will be there. One will give rise to this equation and this will give rise to another equation. So therefore, the second equation will lead to another sweeping matrix. So I will write the final answer. X1, X2, X3 is equal to 0, 0, 0, 0, 0, 0 and X31, X22 minus so if we use this, it means both the modes have been stripped out. So to solve the problem, the same problem, because already the first mode has been solved, for which we know that your first mode omega 1 is 0.425 square root of k by m and x1 is 1.41, 1.71 or something, 71 or 72. This is solved. So therefore, now we should be able to figure out how much is going to be the second mode. Now it involves too much of calculation, we do not want to do it. What we will show just is that x equal to omega square m by k, same kind of formulation. Here is the D matrix and sweeping matrix for first mode into x, and this becomes omega square m by k, in this case 0, 0, 0, minus 0.82, 0.18, 0.18, minus 0.71, minus 0.21, 0.79. This is our final. Now we have to assume something here and repeatedly pre-multiply by this, which is nothing but d into S1. So therefore, this is going to sweep out the first mode and it will now converge to the second mode. If we do it, if we start with 1, 1, 1, it does not matter. What we will be converging to, omega 2 or omega n2 will be 1.18 square root of k by m, and the second mode will be 0.7 minus 1.8. So this matrix actually, this is sweeping matrix. When you multiply sweeping matrix by this, you get this. If we just do the same thing, that means sweeping matrix, if we have used both the sweeping matrices, then that means C1 and C2 0. If we multiply that by D, the equation we will get for the third mode that is the sweeping matrix to sweep out both first and second mode, and your third mode equation becomes this matrix becomes sweeping matrix. Okay, directly you can write. So this is D into S1 is this matrix. If we again assume any value of x to start with and pre-multiply by this again and again, we will converge to omega 3 and third mode will be 1 minus 0.245. Now we have to remember that we have solved first mode and second mode. That's why now we are able to calculate all these terms, because here we need both the first mode terms and the second mode terms. So thus we get all the higher modes by using this sweeping matrix technique. If we solve directly a matrix equation, of course, then we get all the modes and all the frequencies simultaneously, but it is very computer intensive process. So I think what Now you can see that it is very, even if it is simple, but then it takes some time. The question is, are there means or methods by which we can quickly estimate the fundamental frequency, which is generally of maximum importance. So, I think in the next session we will discuss techniques by which a quick estimate of the fundamental frequency or first natural frequency can be found out without going through such detailed calculations.